I will start the presentation now. Hopefully you are hearing this. It's actually entitled The Himalayas, though it's a discussion of India and its passage across the Tethyan Oceans to collide with Eurasia, and hence the building of the Himalayas. Now, we're all somewhat familiar with the portion of Pangaea we describe as Gondwana, and this is one presentation. It looks a little complicated. From 280 million years ago, you'll notice that there are patches of white on all these southern continents, which are actually snowfields or continental glaciation. It was probably much more widespread than is indicated by those residuals that we see today. Australia is fairly well presented, particularly, say, in the Western Australian region, whereas in fact we have a pretty continuous record right across from Adelaide through Victoria and to Sydney, much more so than in the Western Australian areas. Suffice to say, the South Pole was probably a little closer to Melbourne than is shown on this diagram. We believe a matter of a few hundred kilometres or 1,000 kilometres from Melbourne. All these southern continents were glaciated with a massive continental ice sheet, several kilometres thick, up to probably 5 or 7 kilometres like Antarctica today. There's a great deal more shown on this diagram that I won't try and discuss, but there is a black line across Africa, a broken line saying limit of glaciation, so that we can see it got as far up as Arabia and Oman. So that is 280 million years ago, and many of the sedimentary basins show glacial deposits in this period. There are also several zones out to the what is today's north of Australia and north of Greater India. That's what GI stands for, portion of India which is now missing or hidden in the Himalayas. And these blocks moved across oceans as oceans spread and collided with Eurasia to give the various mountain chains of Asia today. Here's another presentation showing clearly that ancient Paleotethys ocean, we should say oceans, because there's a sequence of at least 3 of them, which spread fragments of continent across them from Gondwana to adhere to North China, South China, and to various parts of Kazakhstan, etc. You can see, in fact, Tibet is marked down there below the equator of that time, near where the arrow goes to Tethys Ocean. And the older one, the Paleotethys, lies to the north at this time. So as Tethys Ocean opened, the Paleotethys closed, and Tibet, etc., were carried northward. 250 million years ago, Paleotethys Ocean separated fragments of Gondwana. That's the future Himalayas, Central Asia and Indonesia, from Siberia, Manchuria, and the North and South China plates. You probably have seen this illustration previously. The yellows and browns are the modern oceans of the last 80 million years or so. The greens probably go back to 150 million years, and that's ocean floor formed by volcanism from the spreading centres in the centre of the main oceans of today. The main outline in black is the Indo-Australian plate. The Australian continent has also been outlined here. And of course, India is shown colliding with Asia. Parallel banding within those colours all the colours represent ages at which the last formation or movement of those areas occurred. So the purples in Australia and Africa are the very old rocks, several billion years old. The blue-greens or are older colours too, probably older than about 300 million years, while most of those fresher colours, the browns and yellows, are less than about 60 million years. So we're talking today about that Indian-Australian plate colliding with Asia to form the Himalayas and the Tibetan Plateau in a collision mainly with China or Kazakhstan, etc., to the north. And of course, the Australian plate originally had large areas of the Tethys Ocean associated with it, and some is still disappearing beneath the Indonesian arc, where we've marked the deep sea trench running around Sumatra and Java. And of course, this results in the volcanic island arc following all that way round through Indonesia. The northward movement of the Indian plate continues, something in the order of 50 millimetres a year, and it's still crushing the Himalayas, which are rising today. Now, this slide shows us a series of positions of India, starting with the brownish colour at 40 million years, and then a lighter pink or something of that order at 30, the blue at 20, yellow at 10 million years ago. Actually, the collision with Eurasia or the Asian continent started to occur about 20 million years ago, and the crushing of the Himalayas, shown in dark brown, really satellite imagery, started to occur at that time, 20 million years ago, is going on today. So the main Himalayas are rising at a centimetre a year or so, and there's a crushing action resulting from that 50 millimetre a year movement of the Australian plate northward, or Indo-Australian plate northward. So just reading that, the progression of continental India from 40 million years ago to its collision with Asia 10 to 20 million years ago. The weak crust of Tibet crumpled and was elevated to become the highest plateau on Earth. This is due really to the thickening of the crust and the theory of isostasy, which results in the, the floating of the light and thick crust to a high level. This, of course, is the theory we've often presented of the subduction zones where an ocean is disappearing beneath continental crust. Continental crust is light and will not sink as does the dense oceanic crust. You get a series of major thrusts quite often shown by these blue dashed lines, which result in mountain formation. And these mountains are folded and faulted, and often there's a great deal more deformation and igneous, that is volcanic and deep magmatic or granitic intrusion of magmas that originate from something in the order of 100 kilometres depth, where the asthenosphere meets with the rather more rigid lithosphere. It's the lithosphere and continental crust, essentially, that are moving as a plate. This particular diagram is called a destructive plate margin of the mountain building type, Cordilleran type. Its subduction of oceanic crust along a trench gives rise to mountain building and intrusive or extrusive igneous activity within the continent. That means, of course, granites at 10 kilometres depth or volcanoes at the surface, or all sorts of other features of volcanism. And that's really what's been going on in the Himalayas over the last 20 million years or so. So they're a relatively young mountain range, stretching nearly 3,000 kilometres along that border between India and Tibet. This slide indicates that the range began to form between 40 and 50 million years ago, when the two large plates, India and Eurasia, started to collide. Of course, initially that was oceanic crust, and that was sliding in under what are the Himalayas today, and later it's partly subducted some of the greater Indian continent, but it's mostly crushed it against Eurasia. And this writing says about 225 million years ago, India was a large island still situated off the Australian Antarctic coast, I suppose you say, and a vast ocean, Tethys Sea, separated it from the Asian continent. When Pangaea broke apart about 200 million years ago, India began to forge northward and ultimately closing the Tethys Ocean. And scientists have since reconstructed that northward journey. At about 80 million years ago, India was roughly 6,400 kilometres south of the Asian continent, moving northward at a rapid rate, something like 9 metres a century. When India first rammed into Asia 40 to 50 million years ago, its northward advance slowed by about half this to around 50 millimetres a year, or 5 kilometres in a million years. This collision and associated decrease in the rate of plate movement are interpreted to mark the beginning of the rapid uplift of the Himalayas. The arrows indicate the main directions of movement, and we see roughly located Mount Everest. A geological map is probably much more difficult to appreciate. Let me say this is the northern section of India. We can, on the right-hand side, we can see the delta of the Ganges. And in the north, the red spot, Kathmandu, there's a misspelling in that. And various rock types are coloured for their age, so that some of the older ones here are the browns between 500 and 250 million years, whereas the other colours are illustrated in the key below. So pinks about less than, sometimes greater than 500 million years. The paler blues, not very obvious except up in the top right, are about 250 million years or Triassic in age, whereas the younger group of rocks, Jurassic through Cretaceous, from 150 million years to younger, are shown in the brighter blue, and of course the yellows of the last 60 or so million years. Very complex. The dark lines running across the diagram from west to east are probably sutures where oceans have closed, and certainly some are proven to be so. These are marked by differences in level quite often in the Himalayan ranges due to thrusting southward, having developed on them in subsequent years. I'm just noting here an 8.2 quake hit Nepal in 1934, killing more than 10,000 people in Nepal and India. The earthquakes in 1905 and Pakistan's Kashmir region in 2005 have left behind even higher death tolls, 20,000 and more than 85,000 respectively in 2005. And even this year, there's been a very serious one in Pakistan. So we tend to forget the immense significance of crustal movements and its toll on human life. And this is a three-dimensional block diagram of the geology of the Himalayan front, showing the Indian plate with relatively flat-lying sediments of ages varying really from Precambrian or 600 million years or so through to the present-day outwashed plains from the foothills of the Himalayas. Then there are the thrust structures which give rise to the hills and mountain ridges around Kathmandu, whereas the higher Himalayas, intensely intruded by rocks shown here with little crosses, something like granites or the sources of volcanic rocks. Behind that again is the uplifted and relatively thin sequence of the Tibetan Plateau. This is all dominated by southward directed thrusting as a result of the tendency for the Indian plate to underthrust the Eurasia plate. And of course, there are sticking points along those thrusts where earthquakes often originate. And here, a couple of further diagrams illustrating the situation before collision and after collision, the cross sections from south on the left to north to the right, and looking at the one above, before collision. So we're talking 50 million years ago, perhaps, or maybe 20 million years ago. And the Indian plated very old rocks to sometimes 3 billion year old rocks. And the tip of the Indian plate has suffered significant back thrusting, you might say, from the pressures of the Eurasian plate, under which the whole of this plate is attempted to slide. If we look then at the southern section of the diagram, you can see that these frontal thrusts have, in time, progressed southward over the greater Indian plate, so that you have rising Himalayas today actually overlying Indian plate at depth, whereas the Tibetan plateau, which is significantly rising, overlies essentially the Eurasian plate with very much thickened crust due to the underplating by the Indian continental crust, hence the rising Tibetan plateau. So there's a 50 millimetre a year crushing of the two plates, which is resulting in the rising of the Himalayas and ultimately of the Tibetan plateau. I guess you can make a comparison with ice flows. If they're pushed along by the bow of a ship or by wind or something like that, you tend to get slabs sliding over or under others within the ice flows. Can also be driven, of course, by upwelling currents. But this is a picture rather like the Himalayan thrusts of today. In fact, we can see some, I won't say details, but some indication of these structures by deep seismic interpretations from little sound receiving stations placed out at strategic positions, can intercept earthquake waves at different times as they're reflected off various surfaces to very deep zones of the crust. And you can notice here little interpreted laminations and bandings within that crustal zone. And these have been interpreted as, the Ganges batholith, an intrusive body, and the various thrusts in the forefront of the ranges, right down to the depth in the, really at the level of the moho or the upper mantle, where you can see Indian crust sliding under the Lhasa terrain of Eurasia. More and more detail is being developed from large earthquake recordings, of course, over time. I've just put in now a few photographs from the web. This is a mosaic of almost the entire Himalayan belt. Mount Everest more or less in the centre, and it's apparently taken from the International Space Station on Expedition 8 with the pre-Himalayas in the foreground, northern India, looking at Tibet and over towards the Tibetan plateau. And below it is essentially the same zone of several thousand kilometres, 4,000 kilometres or so, from the so-called Pamian Knot in the west, through Kathmandu, about the middle of the diagram, and extending right over to Bangladesh in the east. Pretty much the same region here from a satellite image, and you can see the front of the Himalayas and the boundary of India, Nepal, and China as it is today, with Lhasa centred just east of the centre of the diagram. Everest is shown with the black arrow indicating roughly just to the east-northeast of Kathmandu. It just gives a general concept of the area. The limit of Bangladesh is also shown below. A bit more from the same diagram, actually, of the web, showing the position of Mount Everest relative to Kathmandu in Nepal. And here's a satellite view of the same general region, the Pamian Knot in the far west, the area of Bangladesh where the Himalayas make a hard turn southward on the eastern side or right-hand side, and there's a very broad band up to a couple of 1,000 kilometres almost of the Tibetan Plateau. Behind it is a big sandy desert, which we'll perhaps say a little later, where some evidence of early civilizations have perished as that area became increasingly arid during the last ice age. The Tibetan Plateau, I'm reading this, is a region of 1,200 to 1,800 kilometres wide, of thickened crust resulting from the collision of the Eurasian and Indian continental regions. The crust is double the normal thickness and thus is more buoyant than ancient crustal areas of India or the regions to the north. Hence, according to the theory of isostasy, it floats higher on the mantle below. Oh, this is an amazing exaggerated topography relief from satellite imagery, with the pre-Himalayas in the foreground, running up roughly about to Kathmandu in the middle, a little bit to the left of middle, and over to the highest peaks in the far distance. And again, looking at a couple of those, or one of those main southward thrusts in the Himalayas of the Nepal region and Mount Everest. And here, this one I found on the web too. It's unbelievable. Look at the train of climbers trying to reach the summit of Mount Everest. It's unbelievable. We should get to know the geologists pretty well, judging by these rockhounds. And Edmund Hillary, on the first climb to the summit there, sampled a fossiliferous Ordovician limestone within just a few metres of the summit, and that's a 450 million year old limestone, rather like ones we see around Melbourne or in central Australia, also Western Tasmania. We see the Gordon limestone along the Gordon River, which is showing very similar fossils to those of the sediments of Mount Everest itself. It's a disaster when you look at that ecologically. And there again is it standing back, and there's an outline of the, the bedding layering, and right up near the top is a creamy-coloured limestone, which is Ordovician in age. It lies on older schists and gneisses at the base of Mount Everest, probably dating back well before the Precambrian boundary at about 560 million years. And the sequence continues with large breaks representing the three major Tethyan oceans right through to 50 or even 30 million years ago. So there's a succession from Paleozoic through Mesozoic to the Cenozoic, but all very complex due to the faulting and folding of this collisional zone, India to Eurasia. Here's a comment here of plate collisions. By 15 million years ago, a third of Tethyan oceans in that region had closed, but the collision of continental India and Eurasia continues at about 50 millimetres per year. In Eurasia, there are indications of repeated deformation throughout the last 250 million years, throughout this entire succession that I mentioned a while ago. In fact, back to 450 million years, we see the closure of the three oceans, Tethys 1, Tethys 2, and Tethys 3, sometimes called Prototethys, Paleotethys, Neotethys, and just Tethys. So several oceans have closed in Central Asia, resulting in the various shans or mountain ranges, the Tian Shan, Pama, the Hindu Kush, and the Himalayan fold mountains, which are the result in the various stands. So there's a portrayal. Imagine that's representing 100 million years ago. You have a strong remnant of an ancient ocean, Neotethys, and that shows a block of country separating from Greater India and possibly Australia to be ultimately closed as the ocean expanded from that dense blue line between Australia and the Neotethys. As that ocean expanded, Neotethys would contract to the north, and that block in brown would have moved northward to be crushed against far north area, Megalaurasia. The writing from the web reads, the megacontinent Pangaea broke up with a series of three Tethys oceans, and then the southern continents began to separate from Gondwana more than 100 million years ago. As the oceans closed, it resulted in a series of Gondwana fragments moving northward and finally welding onto Asia. Two of these continents were Tarim and Cimmeria. Well, Tarim is now located in that broad desert area that I mentioned north of the Tibetan Plateau. Cimmeria has separated again with the crushing of the Tethys oceans to really have its representations from Iraq through Iran, really into the Himalayas themselves. Looking again at some of those major structural features, there are huge faults or suture zones where oceans are closed. Speaking of the dense lines marked as sutures, right up in the Altai Shan, Manchuria, through the Yungar and the Tian Shan mountains of Kazakhstan, into the Kunlun, and finally the Himalaya. Qiantan block in China originated from northern Australia and Greater India, as it did, in fact, the Lhasa block. We have a clear picture of the Indian subcontinent moving like a barge against Eurasia and crumpling up a bow wave, very strong bend in what's called the Permian knot. If we can see just a bit above 3 o'clock, the word Pamir, that's referred to as the Pamir block. Knot, I should say, because of its complexity, surrounded by various basins. Whereas in the eastern side in Bangladesh, you have a great twist in the deformation of the Lhasa block, Qiantan block, where they've been pushed against South China from the closure of the ocean basin to the south. I sketched this on one occasion, and you can see within Myanmar today, I've got a semicircle, that there are two belts of country, Indochina and portions of Burma, etc., or Myanmar, which have been crushed in against Eastern Asia. And they were originally a portion of Northwest Australia, Greater India, and possibly even portions of Arabia, etc., further westward. Three oceans separated these. Ocean A, B and C marked there down the centre line, each successively opened and closed the earlier one. Mesozoic story, that's probably 250 to 150 million years ago, or even down to 60 million years ago. For the Lhasa block and Asian blocks, you have a story of accretion or crushing together and adding on to continent. Paleotethys, Tethys 2 and Tethys 3, which split off Gondwana before India separated. You have the final formation of the Indian Ocean to the south, which is what caused the northward movement of India. And those great slabs of country are regarded as exotic terrains, meaning they're no longer found in the position where they originated. And they're now welded onto Asia in mountain ranges like the Tian Shan, etc. Here's a look-see at that bend in Myanmar, or some of it in Western China. And you can see how the Kwantung and Lhasa blocks are now crushed in the Himalaya, having once been, can I use the word, docile portions of Australia and Greater India, but they've been moved across by opening and closing of oceans and crushed into Asia and Myanmar, as we see that pink colour trending south more or less along the central zone of Myanmar. And younger slabs, portion of the Lhasa block, for example, is crushed in there in the mountain ranges where so much turmoil is going on today in the western portion of Myanmar. And so this shows the terrains, meaning those separate slabs of country, the Indian and Myanmar regions, and the Eurasian Plate border region. The foreland thrust of the Himalayas in Nepal, India and Bangladesh are therefore regions of great instability. Some of these coloured blocks, they're called terrains, are comprised of slivers of Gondwana. The Lhasa block, for example, probably contains Ordovician blocks. Well, it does. These may be 400 to 450 million years old, derived from a continent with offshore Western Australia 200 million years ago, before the opening of the Tethys Oceans. Looking now just at maps of, say, 250 million years ago at the left, we have India, Greater India together, with a slab of country waiting to be separated, which would be Burma and Southeast Asia, sitting somewhere along our northwestern borders, but already a portion of China and the stands in the Shan and Thai terrains being separated by Tethys 2, which is in the act of closing Tethys 1 to the north against Asia. So if we jump again 100 million years younger to 150 million years ago, we find that Tethys 2 is now essentially being closed by the opening of Tethys 3. And Lhasa block, a great slab of Southeast Asia and Burma, etc., is being carried passively across the oceans, closing Tethys 2 beneath Asia on those successive subduction zones until collision occurs. And then, of course, the Lhasa block would be highly deformed by further opening and spreading of the Tethys 3. Ultimately, then the Indian Ocean opened and pushed India rapidly northward to crush these into their present geography. And this reads, 250 million years ago, the Shan Thai terrains were separated off from Gondwana by a second rifted ocean, Tethys 2. And the Burma and Southeast Asian blocks were still part of Gondwana. And here, coming successively younger to 70 million years ago on the left, we have Greater India starting to separate from Australia, and the first vestiges of rifting between Australia and Antarctica, which probably started 20 or 30 million years earlier, but didn't really develop into oceanic crust till about 60 million years ago. The Indian Ocean spreading results in the closure of Tethys 3 on a subduction zone beneath the Lhasa block. Some of it rotated clockwise around the Chinese or the South China block to form the ranges in Myanmar. Looking to the right, at only 10 million years ago, that closure is effectively complete, and we can see those slabs of country rotated and crushed against China, and the more stable blocks, we'll call it the Kazakhstan region and India itself, were protected from much of the crushing by a relief of pressure to the northeastward and eastward. There was a great migration along those dark thrust zones, or they're really sliding faults essentially, which allowed escape of sections of the crust from the regions of intense deformation. And reading that below, with the closure of Tethys 1 and Tethys 2, the Shan, Thai and Lhasa Burma, Southeast Asia terrains were accreted to the Asian plates. By 70 million years ago, Greater India had separated from Antarctica and Australia. At 20 million years ago, the microplates were welded into their present relationships. Perhaps one go deeply into this. Sichuan has been suffering very severe earthquakes. That's in West China. And they're effectively on that bow wave of the Burma invection, or that bend in Burma, Myanmar. There's a tendency for escape of material from deep in the crust, really, or really from the mantle itself, eastwards, because of this immense pressure generated by a collision of continents. Many of the features in Southeast Asia reflect this migration or escape of blocks of country, sometimes from great depth. I don't think we need to go into that in great detail. Suffice to say, the South China block is a very old and stable block, and the weak crust of the sediments above the Indian plate were able to escape in that easterly direction. I'll leave it there and attempt to come back to you for questions. Questions, please.
Wow. It's a very complicated story, and just amazing. Is there any other part of the world such a thing happened, where a continent moves so swiftly?
Yes, it's a very good question. The very swift movement of India is pretty remarkable, I believe, but we don't have good measurement on, say, the collisions of Africa with South America, etc., that occurred 3 times likewise. Bits and pieces left behind, the same in Europe. I don't doubt that certain segments have moved very rapidly. You know, I don't think something we register in the last 30 or 40 million years would be unique in the story of Earth. Yeah, that idea of slabs moving off seems to be gaining popularity. For example, the Baja California seems to have moved off Mexico, and it's finding its way northward. And the belief is it might ultimately crush against Asia, you know, in the region of Japan or somewhere, probably faster than the United States itself will. And the ocean is opening. I mean, the plate boundary between Pacific plate and the southern plates, like the Nazca plate, which is South American region, extends right from the Galapagos up through the Gulf of California, so that slab of country now separated from Mexico is eligible to move as fast as the Pacific Ocean opens.
Fascinating.